In this video, we'll be discussing about divide and conquer approach. So in that, we'll be discussing the general method, the recurrence equation, and solving using Master's theorem. So starting from the general method, so divide and conquer is one of the best known general algorithm design technique. So in this, a problem instance is divided into several smaller instances of the problem, that is the same problem. Here we create subproblems of equal sizes. So these subproblems are solved typically recursively. Sometimes different algorithm is used to solve each subproblem. Okay. So if required, subproblem solutions are combined to get the original solution. So a problem of size n is taken firstly, then you create a subproblem of size n by 2, here also n by 2. Two subproblems are created. For this subproblem 1, you find solution, that is solution to subproblem 1. And for the subproblem 2 also you find a solution, that is solution to subproblem 2. Now you combine these two solutions in order to get the original solution for the original problem of size n. So this is what divide and conquer speaks of. So you are initially dividing, and then you are conquering by solving the problem and getting the solution. Finally, you are combining it. Okay, so this was about divide and conquer. Discussing about the advantages. The first advantage is parallelism. Parallelism means the divide and conquer algorithms, they tend to have a lot of inherent parallelism because these are taking place simultaneously, right? This could be solved at the same time. This can also be solved at the same time. So parallelly you are solving it. So that is one of the advantages. Then next advantage we have is cache performance. So once a subset fits in cache, the standard recursive solution reuses the cache data until the subproblem has been completely solved. That is, this divide and conquer technique can solve difficult problems pretty easily by improving the cache performance. Then we have, it also allows solving different and impossible looking problems also. So this technique could be considered to give efficient algorithms. The disadvantage here is, at times, we have discussed that the subproblems are solved typically recursively, right? So at times the recursion could happen slowly. The pace of recursion could be slow. Sometimes it can also be complicated because you are because you are dividing the problem, right? So it can be complicated as well. The same subproblem can occur many times, so it needs to be solved again and again and again. So that is one of the disadvantages. This was about the general method. Here we discussed about what is divide and conquer, this flowchart of divide and conquer, how it works, what are the advantages, disadvantages. Let's move on to the control abstraction of divide and conquer now. So discussing about control and abstraction, this is a generalized algorithm for divide and conquer. So here, if the problem is small, then return solution directly. Okay, P stands for problem. Else, divide the problem into smaller instances, P1, P2, P3, so on. Apply divide and conquer to each problem, yes, and return combining all these problems as all these solutions as one solution. So that is what algorithm for divide and conquer speaks of. Here you are recursively using the same algorithm. You're recalling the function again and again for subproblems. If you can see here, so we had, if the problem is small, then you can solve it directly. If the problem is small, then solve it directly. That is, you get solution for the problem. If the problem is big, then divide the problem into smaller problems, P1, P2, P3 and so on. Now apply divide and conquer to each problems. That is, this algorithm, D and C to P1. Okay, you solve for P1, D and C to P2 and so on. After that, you are returning a function combine. That is, you are combining all these. So this is what the algorithm speaks of. Here we have the recurrence relation for divide and conquer. That is T of n, time taken for dividing and conquering on any input size of n. G of n is to get time taken to get answer directly for small problems. So here the time taken to divide is T of n. To get the answer for smaller problem is G of n. And F of n is time for dividing problem and combining solution to subproblems. So here we can write T of n. The total time taken to solve a problem is equal to G of n. Directly getting the answer if the problem is small, size of input is small. If not, we apply D and C for each of the subproblems, that is N1, N2, N3 and so on. and we also add f of n, because f of n needs to be considered, that is, you're dividing the problem, right? Even that time should be considered here. So this was about recurrence relation for divide and conquer. Now we'll be looking into general divide and conquer recurrence. So generally, an instance of size n can be divided into b instances of size n by b, yes, with a of them needing to be solved. So a needs to be solved, and the problem is being divided into n by b parts. So here a and b are the constants, where a is equal to or greater than 1 and b is greater than 1. B cannot be 1. If b is 1, then you'll have the same problem, right? The size of problem is n. You'll be remaining with n itself. So assuming that size n is power of b, n is equal to b power k. To simplify our analysis, we obtain the following recurrence for running time t of n. That is, this particular general divide and conquer recurrence relation is pretty important, because we'll be using this in Master's theorem. Okay, so we have two ways of solving the recurrence relations. One is substitution method. In substitution method, you are repeatedly make substitution for each occurrence of the function t in RHS until all such occurrences are disappearing. That is, you solve all the subproblems here. That is what we do in a substitution method. Next, we have a Master's theorem. So Master's theorem is pretty important from exam point of view. It will be asked in internals, or it could also be asked in the final exams, GATE, everywhere. So in Master's theorem, in a recurrence equation, t of n is equal to a into t by n by b plus f of n. We can write it as t of n is equal to at, in bracket we write n by b plus theta of n to the power k log p of n. So this is the recurrence relation which we have discussed previously. Here the conditions are a should be greater than or equal to 1, k should be greater than or equal to 0, b should be greater than 1, and p is equal to real number. So these are the constants here. If you look in the textbook, they have given short formulas. Only 3 formulas are there, but then those 3 formulas are pretty confusing. So here I have 3 elaborate formulas, those 3 formulas only, but then we have elaborated here. So if a is greater than b of k, so here they say that any given relation is, if it is of the form t of n is equal to at n by b plus f of n, then you can you consider a here and b here. So if a is greater than b power k, then t of n is equal to theta of n log a to the base b. So this is what, if a is greater than b power k. If a is equal to b power k, now we'll look into the real number part, that is p here. So if p is greater than minus 1, then this is the formula. If p is equal to minus 1, this is the formula. If p is less than minus 1, this is the formula. Then if a is less than b power k, in that also 2 conditions are there. If real number is, if p is greater than equal to 0, then this is the formula. If p is less than 0, then this is the formula. I would say that if you understand these formulae thoroughly, you can solve any sort of problem. Okay, so let me start with the first problem here. That is, I have t of n is equal to 3t. In the bracket I have n by 2 plus n square here. Checking this with the standard recurrence relation, I'll write the standard relation t of n is equal to a t here n by b plus, I'll write the function here. This is the function, right? F of n part is the function. Now this is the recurrence equation which is given in the question. We have to write it of this form. So writing it of that form, I get t of n is equal to a t n by b as it is. F of n should be written as this form, that is theta of n power k. N power k. What do I have n power k here? I have n square, right? And here I have log p of n. What is log p of n? In log place, I don't have anything here, right? So log place I have 1, considering this as 1, because n power k, here n square is there, right? So if I write k value is 2 here, yes, and then a value is, comparing this, 3t, a is 3, then b value is n by 2, b is 2. So I've got a value, b value, k value. Now I'll write p value also. P value should be 0, as there is no log value here. So I'll write 0, because there is no log value here, right? So next I have to check conditions here. So if a is greater than b power k, let me write it here. 3 is greater than b power k, k is 2 square. So I get 3 greater than 4. No, this is not true. Next I'll check a is equal to b power k. A is 3, B par k is 4. No, it is not possible at all. Then I'll check the third condition. A is less than B par k. Let me check. A is 3 here, 3 is less than 4. This is satisfied. So I have to look into the third set of formulae. In third set of formulae, there are again two possibilities, that is P is greater than or equal to 0 or P is less than 0. So I'll consider the first one, because P is equal to 0, right? We have taken P is equal to 0. So P is equal to 0. I will write this formula first, that is T of n is equal to theta of n par k log P of n. That I can write it as theta here, n par k. What is n value? N value, there's nothing n value, right? I'll write n as it is. And k value, what is k value? Square log p. Log p. P value is 0 here. Log 0 power n. So this, it'll go to 1. It'll become 1. So I'll be left out with theta into n square multiplied by 1. So I have theta of n square as the solution. So this was for this particular question. Now let me look into the second question here. Second question here, that is 16t n by 4 plus n. Comparing this with the standard formula, T of n is equal to at n by b plus theta of n power k log p by n, log power p by n. So comparing, I get a value as 16, b value as 4, right? And k value, here I have n and here I have n power k. N power k, here just n means n power 1, right? So k value is 1 and log value is not there, so p is equal to 0. Now I'll check the three conditions. A is greater than b par k, is equal to b par k, is less than p par k. So first I'll start with A is greater than b par k. What is A value? 16. 16 is greater than b par k. B is 4, k is 1. So this condition satisfied. So this is satisfying, right? So first formula is obeying here. So I can write the formula as T of n is equal to theta of n log a b. So here I will write it. So here I'll substitute the values. So it will be theta of n as it is log a. What is a value? 16. 16 is above. And what is b value? B value is 4. So I can further write this as theta of n into log 4 square by 4. So this equates to this. I can write it as theta of n square. Okay, so this is the solution, the time complexity. If I solve the recurrence relation, I'll get this solution. Next I have the third question here, that is T of n is equal to 2tn by 2 plus n log n. So here we have log also. Let's check. So T of n is equal to at n by b plus theta of n power k log power p and n. So comparing a value, I get 2, b value also 2 I get, k value here n log n, so n power 1. So k value is 1, p value, what is p value here? Log is there, no? So p value I'll take 1. Okay. Now b par k, what is b par k value? B par k value is also 2. Here a value is 2, b par k value is also 2. Then I should look at the second condition, that is a is equal to b par k. Now I should check p value also. P is greater than -1, p is equal to -1, and I have p is less than -1. So p is equal to -1. Okay. So this I can write. So p is equal to 1, right? P is equal to 1. That is p is greater than -1. So this condition. So I'll get T of n as theta of n power k log p plus 1 into n. So that is, I have theta, k value is 1. So n, it will be as it is. Log of p value is 1. 1 plus 1 is 2. And n here. So it is theta of n log to the power 2 n. So this is the solution for this particular recurrence relation. Now let's look into the next recurrence relations. So I would say that if you understand this master's theorem, it will be very easy to solve the recurrence algorithms, recursive algorithms, which we have discussed in previous videos, and analyzing the recursive algorithms. Let's look into this question quickly. So I have Tn by 2 plus 1, writing the recurrence equation. T of n is equal to Atn by 2, Atn by b plus theta of n power k log power p and n. So comparing a value, I will get as 1 because nothing is there here, means it is 1 only, no? B value I'll get it as 2, n by b, n by 2, and k value I'll get it as 1, and p value is 0 because there is no log value here. Now quickly I'll write b par k value also. B par k is 2 itself. So from this I can write that a is less than b par k. A is less than b par k means I should look at the third condition. Looking at the third condition, we have two formulas here further. That is, I should look at the p value also here. So if I look at the p value here, I have p is equal to 0. If p is equal to 0, what will I write? I will get t of n is equal to theta of n par k log p into n. So theta of n par k, k value is 1, and log p 0 of n. So I would be remaining with theta of n. So this is the solution. Now looking at the next problem. So if you solve these problems like 2-3 times, you can quickly solve any given equation. You can quickly solve it. T of n is equal to at n by b plus theta of n par k log p n. So a value I have 2, b value I have 2, k value I have 1, and p value I have 0, and b par k value, that is 2. Here I write a is equal to b par k. A is equal to b par k and p is equal to 0. That is, p is greater than minus 1. So if p is greater than minus 1, I have the condition t of n is equal to theta of n par k log p plus 1 into n. That is theta of n par k. K value is 1. So n, and here log p value was 0, right? So here I have 1. So log n. So here 1 will come. So it is theta of n log n is a solution. Looking at this question, we have comparing this with the standard the recurrence equation, that is t of n is equal to at n by b plus theta of n par k log p n. So I get a value as 4, b value as 2, and k value here n cube is there, n par k. So k value as 3, p value as 0. Now b par k, 2 par 3, that is 8. Here I can write that a is less than b par k. So when a is less than b par k, I should look at the third equation. In third equation, p value is also 0. So I'll get the equation as t of n is equal to theta of n par k log p n. So it will be theta of n par k. K value is 3. N cube log p 0 n. So this will go to 1. So I'll be remaining with theta of n cube as the solution. So let's quickly solve for the other three recurrence equations also. So here t of n is equal to 2tn by 2 plus n by log n. So here I can write t of n is equal to at n by b plus n par k into log p n, theta of log p n. So I get a value as 2, b value as 2, n value as k value as minus 1 because it is n by k value as 1 only, and p value as minus 1 because it is in the denominator, right? So I'll write minus 1 here. So this if I write b par k value, it will be 2, and a value is also 2. That is, a is equal to b par k. So this is the second equation, right? A is equal to b par k. Next, the sub condition is p is equal to minus 1. When p is equal to minus 1, I have the formula as t of n is equal to theta of n par k log into log n. So solving this, theta of n power 1 log of log n. So it is theta of n log of log n. So this is the solution part, the complexity. Now let's look into this question. So we have, I'll directly write the AB values. So comparing this with AT n by v plus n par k log p n. So I can get A value as root 2, B value as 2, K value as 0, and P value as 1. So if I write B par K value, I get 2 par 0, that is 1, and A value under root 2, that is 1.414. So if I compare, I can write A is greater than B par K. So if A is greater than B par K, the first condition, T of n is equal to theta of n log A by B. A and B. Okay. So I'll substitute the values. N log A value is 1.414 and B value is 2 here. So if you solve this part, you get theta of n and n par half. So this is the solution for this question. Next I have this. So this recurrence equation, the last one, I can get A value as 3, B value as 2, K value as 1 by 2, and there is no log part, so p value is 0. So b power k, if I write 2 power half, what is 2 power half? 1.41. That the same thing, 1.414. Okay, so I can write a is greater than b power k. If a is greater than b power k, the same formula which we have used here, t of n is equal to theta of n log to the base a n. In the bottom we write b, which is theta of n log a value is 3, b value is, what is b value? 2. So this is the solution. Master's theorem. Now we'll be looking into substitution method. So we'll solve this and we'll compare which one is easier, which one is quick to solve, because in exam they might either ask substitution method or Master's theorem. So in case of like complex algorithms like merge sort, quick sort and all, if you have to calculate the analysis part, time complexity part, you can directly use Master's theorem instead of going through substitution method. If and only if it is mentioned in exam, then use substitution method. Let's start from substitution method. So first question they have given, t of n is equal to 2t n by 2 plus n, and t of 1 value is 1. We need to solve this using substitution method. So I will take this thing as equation 1, n by 2. So t of n by 2 is equal to 2t n by 2. By 2 again I am writing, so it will be n by 4 plus here n is there, so n by 2 I wrote. Now I'll substitute this in t of n value. So substitute t of n value here. So it will be 2t, okay, 2 will be outside, so 2t n by 4 plus n by 2, this is the internal part, plus n. So I'm substituting this in equation 1. Okay, so I got this. Solving this, I would get 2 square t n by 4 plus n by 2 t plus n by 2 plus n. So further I can write it as 2 square t n by 4 plus 2n, n by 2 plus n, 2n. So I'll consider this as second equation. Now I need to find value of t n by 4. So finding value of t n by 4, I would get it as 2t n by 8 plus n by 4. So third equation, substitute it in the second equation. So I'll have t of n as 2 square 2t n by 8 plus n by 4, and outside this 2n is as it is. Now further, if I take this 2 outside, it will be of the form 2 cube t n by 8 plus 3n. So if I continue doing the same for ith value, I can write t of n is equal to 2 power I, by looking at the trend which is being followed here, t of n by 2 power I plus I of n. Okay, here they have told that t of 1 is 1, right? So I'll consider n by 2i as 1. So if I consider n by 2i as 1, I can write n is equal to 2i. So further I can write I value as log n to the base 2. So I have obtained the I value. Let me substitute the I value in the general equation. So I would get the general equation as t of n is equal to n into t of n by 2 n plus log n to the base 2 into n. So t of here I have just n by n. So n by n value 2i value is n, right? So I have substituted n here. N by n it becomes 1. So t of 1 value is 1, I know. So I'll be left out with n here, n plus log n to the base 2 into n. So this can be further written as, time complexity can be written as t of n is equal to n plus n log n to the base 2. So this is the time complexity. It can be written as order of n log n to the base 2. Okay, so this was about the substitution method. But then if you would have used Master's theorem here, you would have solved it in 2-3 steps itself. So let's look into the next question here. We'll be looking into the next question. So we need to solve t of n is equal to t of n minus 1 plus n, and t of 1 value they have specified it as 1 using substitution method. So I'll take the first equation, t of n is equal to t of n minus 1 plus n, as the first equation. Now I'll substitute t of n minus 1 here. I'll generate an equation that would be t of n minus 1 minus 1. It will be n minus 2 plus n minus 1. So now that this t of n minus 1 is I've obtained, I'll substitute it in t of n value. So I would get t of n as t of, in place of n, I'll write n minus 1. So it will be t of n minus 2 plus n minus 1. Right. So this is the internal part. Next I have plus n outside. Right. So this is for t of n value. If I solve this further, I would get t of n minus 2 plus, if I multiply this, if I solve this, I would get 2n minus 1, n plus n, 2n minus 1. Okay. Next I have t n minus 2. I will find value for t n minus 2 and substitute in t of n. Let me see. So here I would get t of n minus 2 is there, n minus 1 in n minus 1, right, in this. So I will get n minus 3 plus n minus 2. I will substitute this in the above equation. So I will get t of n minus 2 as t of n minus 3 plus n minus 2. This is the internal part for t of n. So here it is t of n only. This is internal part plus 2n minus 1 should be outside. This 2n minus 1 I have obtained here. Here I have written it here. Okay. Next I'll write for, I'll simplify this and write t of n would be t of n minus 3 plus 3n minus 3. So if I further write it for t of n minus 4, it would increment to t of n minus 4 plus 4n minus 4, and it keeps on repeating. Now that we have understood the pattern here, we can write for ith value as t of n is equal to t of n minus I plus 4i minus I, for ni minus I. So this I can write as t of n minus I plus I of n minus 1. So if you solve this, I can write it of this form, right? N minus 1 and I would be common between these two. So I took it out. Okay. Now I will take n minus 1 as 1. So n would be I plus 1. So substituting this form, this values here, t of n, I would get it as t of n value is I plus 1. I plus 1 minus I plus I value is, here t of n minus I it is. So here I write I value is n plus 1, right? So here I have n plus 1 and here I have n minus 1. I'll keep n minus 1 as it is, okay? So if I solve this, plus n minus n cancel, I will get t of 1 plus n plus 1, n minus 1 is n square minus 1 square. So here I have t of 1 plus n square minus 1 square. T of 1 value we know it is 1. So I wrote 1 here. N square, I have written n square minus 1 square is 1. So plus 1 minus 1 cancel, I would be left out with n square. So time complexity for this given recurrence equation is n square, theta of n square. So in this video we have covered the substitution method. We have made use of Master's theorem, understood Master's theorem, solved problems on that. And then we have discussed about the general divide and conquer recurrence equation, the general method. So if you have any doubts, do let me know in the comments and subscribe to my channel. Thank you.